let's start the last section. Welcome back to the second modeling webinar, sorry, about, in this part we are about to start the third section, which is about an example where I will show you the incoherent feed-forward loop. Very short and simple model that we did on that circuit, and then I will show how to relate with data. There is a question in the Q&A from the previous seminar section. Sorry, I will go on with this and I will answer at the end. Okay, so we keep in schedule with this. Okay, so let's keep going. Sorry for that. So for the ones that it's a quite famous circuit, let's say, motif, but for the ones that they don't know, I will introduce it. The incoherent type 1 feed-forward circuit, or I1FFL, is a circuit that it has two paths. There is an indirect path and a direct path. The direct path is responding to an input directly to the output. So if you put something that goes up here, then the direct path makes the output to go up. And then there is an indirect path, which in response to a stimulus, it has a negative response in the output, which means it makes it go down. But this path, it's a slower path because it has two elements. It's made by two elements, so it's a slower path, and it reaches the output later than the direct path. These two, if you put these two together, the resulting behavior that you have from this circuit is that when you have a change in the input, the output responds going up and then quickly goes down. It goes back again down. Okay, and this, if when it goes back down again, it goes to the previous level that we had before, then is what is called perfect adaptation, and this behavior in general is what is called adaptation. There is a change in the environment, in this case the input of the circuit, then the output changes. This in general in bacteria, in living organisms, there are many circuits like this, and in general this is a signal that kicks off a downstream process of signaling or whatever. And then what happens is it goes down again. And if it goes down again, as I said before, to the level prior that you have previously of the stimulus, then it means that it didn't change. It changed dynamically responding to the input and then went back to the value that you had before. And this is interesting, for example, this happens in homeostasis, for example. If you change the environment from, I don't know, from the south of Patagonia, which now is very cold, to the north to Spain, where am I now? It's very hot. The body temperature is, if everything goes good, is always the same. So, but you may have a little change when you change the environment. So sorry if I got messy with the example. It was to try to clarify. Okay, so we have this circuit. Let's have a look to a more detailed implementation, a synthetic implementation of this circuit in the lab. We can make it work with 3 genes. The direct path is with a promoter that is sensible to a transcription factor, which is based on Luxar and AHL, which is a molecule that you put from outside. So the input, the stimulus that we will give to the circuit is the amount of AHL. This is it's a famous system from Birio-Fischeri and from the quantum sensing. Depending on how much AHL you have, you will have different levels of activation of this promoter. So this is the direct path. And then the indirect path is another gene which has this same promoter, which gets activated when we have Luxar AHL, and this produces the CI protein, which inhibits or represses this former promoter here. So it goes up when you put the stimulus, then this one also go up, and it represses the promoter of the GFP, making it go down again. So that's one implementation of this circuit. If we make a model of this, don't freak out. Just take a look at this with calm. Sorry, I'm not using the same letters than before because this was previously done. It's the model that I did a few years back, but it has the same essence and the same idea behind, which is here is the Luxar, as we saw in the sketch, is constitutively expressed. So we have this is the what we get from the previous week, the expression of the constitutive expression, which depends. PR is the translation, copy number, transcription rate, degradation of the mRNA, and dilution of the culture. And then the protein DR has a decay and a dilution from the growth. If you look at the last equation, this is the growth equation, which is exponential growth with specific growth rate mu, and n is the number of cells. And then we have a maximum capacity of the medium, which makes the famous exponential and then stationary phase curve that we are all familiar with. And then these two guys are the CI protein, which is PLAX promoter, and the GFP with the hybrid promoter. If you look, this part is the same than this one, which is the part of the promoter that responds to Luxar and AHL. And this part, which is a repressor, because here it has 1 and 1, is the part that responds to the repressor. This part is the repressor responding to CI. There are a few questions. One is that if the mu in the first equation is the same one as in the last one, yes, mu is the same in all the equations, and is the specific growth rate of the culture, which is making the amount of proteins to be diluted, in the sense that if you have a growing amount of cells and the same amount of protein, then you will see less and less amount of protein per cell, which is what we are modeling. That's why we get this term related to growth here. And okay, and there is another question which says, if it returns to the pre-stimulus value, does this allow you to repeatedly trigger the circuit in a short time span to keep producing a response? Yes. If you look in the, I can point you to the right papers, but the one from Ron Weiss a few years back, if you do that, you can have like a force oscillator. If you keep putting input repeatedly, you can have firing the peaks one after the other. You need to be careful, and that's one thing that they found in the paper. If there is a time that you need to wait until the system goes really back to calm, let's say, before you put the second stimulus. But yes, the answer to the question is yes. Okay. So again, if you look, they look big expressions, but in general, they are the same that we were seeing before. This one is the hybrid promoter, and it's a little bit bigger, but it has two terms that we know, the term from the repressor and the term from the activator. And here I'm putting all these detail because when you design, you may be able to change different, for example, if you change the amount, the promoter for Luxar, then you will change the value of the amount of Luxar that you have, will change this guy here. So to have a little bit of detail, you can make the model more detailed. But that depends on what your interests are and what you want. There is another question here. It says, general modeling question. What could be the most complicated possible thing that you could model with an ODE? Wow, that's a very big question. But anything that doesn't, so ODEs don't take into account space. If you need something to have a problem that needs to take into account the space. For example, if you model how the colony grows in a petri dish, or how a fluid moves in a pipe, then the ODEs are not the ones that you're looking for. You need partial differential equations for that. But other than that, if you are modeling any other system that doesn't take into account the distributed space, you can model it with ODEs. Anything. Tell me something and I will tell you how to model it. Of course, the level of detail that you want is what is more important. You simply, for example, the COVID pandemic with the SIR models, those are ODEs. You can make a simple model with 3 equations, or you can make a much bigger model with many equations. But that depends on what you want to get from the model. That's the most important question, sorry, that you need to ask yourself before starting with the sometimes very difficult task of modeling is, what do you want to get from the model? So in this case, let me put it into the example exactly. In this case, we wanted to know how to build the circuit, which parts to use in the lab to make it behave like I said before, like this. Sorry. I want it to behave like this. When I put AHL, it has a peak, and then it goes back. And if I put here the part that I didn't mention, the change fault detector, if I put a higher value of the stimuli, I want the peak to be higher. And if I put a small change in the input, I want the peak to be lower. So I want it to be also sensitive to the amount of change, not only sensitive to the change, but also to the amount of change. So that's why we build the model, because we wanted to know how to construct the circuit. So let's say that we select values for these parameters. That is another problem that we can deal or try to find later. But one of the ways is measuring, calibrating, and doing as I did before, the estimation of parameters. Let's say we select some parameters for all these, some values for all these parameters, and we make a simulation. And this is the one I have here. The growth is in numbers of cells, because later I will like to compare it with the calibrated particles that I get from the OD measurement in the lab. And here I have the plot of how GFP changes. And in this point of time, I'm putting a change in the level of AHL, and my system is responding. So good. I have the first part, which is, it looks good. If you look here, it's not going back to the exactly same place that it was before. It's going back a little bit higher than before, but it's still good. But what was the problem of this implementation of these numbers of the parameters? If you change the amount of AHL that you put, if you put 10 nanomolar, 100 nanomolar, 1000 nanomolars, the height of the peak, it was always the same. So our construct was not able to determine the different levels of AHL. It could see if there was a change. So if there is no AHL, sorry, and I put AHL, then there was a response, but the response is not sensitive to the different levels of the change. So what we did, we start playing with the different parameters, and actually we did an optimization to try to minimize the error between the different levels more complexly. I can, if someone wants the detail, I can give it later. And we found that the hybrid promoter was having a KD which was too low. And we were on the on the higher part, on the saturated part of the promoter. So it was sensing from nothing to some value of AHL, but we were jumping up to the other side of the Hill function, and we were not being able to make a smooth path through the linear part of the Hill function, which is the sensitive part, the part that changes. So we learned that we had to have a promoter, a hybrid promoter with an increased KD to be able to sense the values of the concentrations of AHL that we were putting into the system. And once we did that, we were able to get detection of the changes in the induction levels, and to have the peaks with different maximum values depending on the level of AHL we put it into the system. And we did that by simply changing the copy number of where we put this promoter. We changed that, and with that we increased the KD in the amount that we needed, and we had a system now that was ready to be implemented in the lab that presumably had the response that we want. So with that information, we went to the lab. We made these two plasmids with the 3 elements. We put them into an E. coli, and here is a microscope image of the E. coli after induction. So they are green. This is working. And then, oh, sorry, I thought I was going to show the experimental data. I will show it later. With the experimental data that we got, we did a calibration and we calibrated all the measurements. And so if we put the same input, AHL, to the model and to the real circuit in the lab, and we compare those things, we will be able to get values for those parameters in the model to make it represent the output that we had in the experiment. And to do that, again, we did the estimation of the parameters, the minimization of the error. In this case, it's a bigger expression because we have the error along time. And to make the story short, we can, if you have more than one objective that you want to minimize, in this case, we had different scenarios, which are the different experimental, the different data from the experiment for different levels of induction of AHL. So we had different scenarios, what we call here. So we wanted to minimize all of them at the same time, and that becomes a multi-objective optimization problem, which we solved with the algorithm that is down there. If someone wants more detail on how to use multi-objective optimization for parameter estimation, let me know. I can help you later. And so after doing this, and trying to make this long story short, we found this. So the dots, the error bars are too small that we don't see it in this case, but they are not from different days. We want to do it for different days and to have a bigger error bar representing the good variability among days. But so this is from one day, different replicas, and the error bar is very small. And so what we can see in different colors are the different induction levels of AHL, if I don't remember correctly, 2 nanomolar, 10 nanomolar, and 20 nanomolar. And the full line that we got here is the result of the simulation. Of course, it's not perfect. The dynamics are not exactly the same, but we are capturing the different levels, and we are capturing the fact that this goes up and then down, and they are going down to the same level. So it's not a perfect fit, but we are getting information of the model. What is important is that we are not fitting the curve, but we are fitting the mechanistic information that we put into the model when we build it. We are comparing that with the experimental data that we get from the lab. So that's very interesting. And to make a summary just of what we learned today, this is the last slide. The important thing that I wanted to show you is that with doing the appropriate modeling before going to the lab and constructing, which is something that is happening these days because of the pandemic of COVID, take advantage of this time that you have not been able to go to the lab and do a good modeling and try to solve the problems beforehand going to the lab. For example, what I was showing in the first section, the different ranges of the input of the different systems that you connect, they have to be compatible. If you connect systems that don't have compatible input and output, the system will not work. Or in this case, for example, the first guess that we had for building the circuit, it was making the peak, but it was not responding to different levels of the changes in AHL. With the model, we were able to find what change we need to do to be able to find and to make the system work as we expected, responding to the different levels of AHL, okay? So this will be all. If we have any question, let me change to the last slide. All the files, the slides, and the MATLAB scripts that I used to make this webinar will be available, as I said before, in our Git repository. And thank you for listening. I hope this gave you a little bit of information and it increased your curiosity about modeling, and we are open to answer any kind of question you have. And few reminders: the next week we have the webinars from Jake talking about calibration. Very important, very interesting. If you want to relate the models with what you get from the lab when you will be able to do that, please go and see those. And the measurement committee is having office hours, and there is one today at, I think it's
not today, it's every 2 weeks, so the next office hours is next week.
Okay, so next week, checking the web, where is the time. And anyway, if you have any questions, please send emails to the measurement committee or to me if it's directly related to this. And thank you very much.